In the previous lecture, we have discussed in very detail the DC Josephson effect. Now today we are going to see the second part of the lecture in which we will see the discussion on AC Josephson effect. Actually, in case of DC Josephson effect, you have seen that when the two superconducting material, as you can see in this figure, which have been marked by 1 and 2, these are the superconducting materials, and these are separated by a very thin insulating oxide layer, which I have marked by this dotted region. And no voltage is applied across this junction, which is actually called weak link. Then a DC current flows due to the Cooper pair from one region to the another. But what will happen when a DC source is connected between the insulating layer? You know, since the material between these two superconductors are insulating, so we can apply a DC source. Normally, in general theory of current electricity, you know, when in a circuit there is a DC source, a DC current flows. And in case of AC source, AC current flows. But here, surprisingly, it is seen that when a DC source, let us say, of which will supply a voltage V, is applied between these two superconductors across this insulating junction, then it is seen that an oscillating current flows from one region to another. That is, an AC current flows. Source is DC, but the supercurrent constituted by the Cooper pair in this case will be AC. Actually, this phenomenon is known as AC Josephson effect. This is all due to the surprising nature or exciting nature of superconductor. It is never possible in case of normal metal, but when you will connect a DC source across this insulating layer, very thin layer, sandwiched between these two superconducting materials, and then actually AC current flows while we apply the DC source. Actually, this phenomenon is known as AC Josephson effect. Okay. Actually, it is seen that the current which flows, in this case, which is of alternating nature or oscillating nature, has a frequency nu, and that nu depends on the applied voltage, and it is given by nu equal to 2 EV divided by H. Or if you will define the cyclic frequency or the angular frequency, that will be 2 EV divided by H bar. I have written this expression directly. This is frequency of the resulting AC. But when we will discuss later on the proper theory, then you will see how we can say that the frequency of the oscillating current will be this much. Okay. In fact, what's the reason behind this? In fact, this is caused by the coupling between the wave in one superconductor and the wave in another superconductor. Okay. Crudely, it is just analogous to the classical beat phenomenon in the superposition of two waves of different frequencies. You know, when two waves of different frequency, let us say omega 1 and omega 2, get superposed, then definitely in lower classes you have studied, in particularly in chapter acoustics, a very important phenomenon that is called beats, and after the superposition of these two waves, a resulting wave is produced, and and there will be a waxing and waning of intensity with a frequency which is given by omega 1 difference omega 2, which is called bits frequency. So this phenomenon is just like that. This is that classical phenomenon is analogous to this quantum mechanical phenomenon. Okay. Actually, the wave functions of a Cooper pair on the two sides of the junction differ in energy by 2 eV. We will also see how we can say that the energy of the Cooper pair in two regions will differ by 2 eV. We will see later on. Okay. And if the energy difference is 2 eV, what will be the frequency difference? You know that E is equal to h nu, and so nu will be simply equal to E over h. And if E, which is the difference, you can write also a difference of energy. If this difference is equal to 2 eV, then frequency will be 2 eV over h. Okay. Now, since the charge density and the current, only depends on modulus of psi square. This is the probability density, So the individual wave frequencies are not observable. It means you can't observe the individual frequencies whose difference is given here. Actually, we can only observe the difference of the frequencies, or you can say that when the waves are coupled, the amplitude is modulated by the beat frequency, and which is equal to the frequency difference. Okay. In fact, when we will take this V equal to 10 to the power minus 6 volt, or you can say that 1 microvolt, then from this result, if you will calculate the value of frequency, you will see that this will be almost equal to 483.6 megahertz. Okay. From this formula you can obtain it. Actually, if we know the frequency, it is clear from this result that we can obtain the ratio of H and E. So H by E is also determined by using this AC Josephson effect. All these things now we will see by a proper theory, by a quantum mechanical theory. Just you have explained the DC Josephson effect on the same line, on the same way. It is possible to explain this AC Josephson effect too. Okay. So now we are going to see the theoretical part of this AC Josephson effect, and it will be very interesting because you have already learnt about the explanation of DC Josephson effect, and this explanation is just analogous to that. So it will be very easier to understand it because you have already learnt the explanation of DC Josephson effect. Okay. All the facts which I have just discussed, for your convenience, I have note down these things here because then you can note these things in your notebook, because several of my viewers always ask me to provide the PDF form of notes, but I always reply them that there is no need of PDF of my video because my videos are already in very detailed form. I have actually write all the facts, so you can pause the video, note down these things in your notebook, and that will be a very good notes for your examination purpose. Okay. So let us see what I have explained. I have mentioned it here. You can see in a Josephson junction, two pieces of superconducting material are separated by a thin, whose thickness is almost 2 nm, insulating oxide layer. Okay. The Cooper pair can tunnel through the through the junction junction or weak link, giving a current from one superconductor into other. If a DC voltage, mark it, if a DC voltage V is applied across the junction, an AC current, source is DC but current is AC, is resulted. And this phenomenon is called AC Josephson effect. And the frequency of this oscillating current is given by this formula, which, and you can see the frequency is proportional to V. So when V is 0, then frequency will be 0. It means current will be not 0. Current, in that condition you have already learned, there will be a DC current with 0 frequency. But when we apply a DC source or DC voltage, we have an oscillating current or AC current whose frequency is given by this. We will actually prove this result later on in this lecture when I will discuss the proper theory. Actually, this AC Josephson effect is caused by the coupling between the wave in one superconductor and the wave in other. It is analogous to the classical beat phenomenon in the superposition of two waves of different frequencies. The wave functions of a Cooper pair on the two sides of the junction differ in energy given by this. You can see delta E equal to EV minus EV. Actually, EV is the potential energy of a Cooper pair in one side, and when it is in other side there is a potential drop of V, so its potential energy will be minus EV. And so the change in potential energy of the Cooper pair is 2 EV, and therefore the frequency difference will be equal to delta E over H, and that is equal to 2 EV over H. Okay. Now the charge density and the current only depend on this probability density. Mod of psi square means probability density. So the individual wave frequencies are not observable. Okay. However, when the waves are coupled, the amplitude is modulated by the beat frequency, which equals to the frequency difference. Okay. And as I have told you that when we take a particular value of V, which is 10 to the power minus 6 volt, that is 1 microvolt, then from this result you can see that mu comes out to be this much. Okay. So the measurement of the frequency of AC Josephson current can be used to a very precise convenient method for measurement of voltage. Okay. If you measure the frequency, you will be able to measure the voltage, and if you know the value of voltage, you can measure the frequency, and if you know both voltage and frequency, you can measure the value of H over E. Okay. So these are the actually utilities of this AC Josephson effect. Okay. So what is this AC Josephson effects? I think now you have clearly understand. Now, by a proper theory, we are going to explain this AC Josephson effect. And as I have told you earlier, that this explanation is just equivalent to the explanation of DC Josephson effect, which you have already learned. So this session is going to be very easier to understand to you. Okay. So now let us consider a DC voltage V, as I have shown in that figure you have seen already, is applied across the Josephson junction. Okay. And it is possible to apply the DC voltage. Why? Because the junction is an insulator, so we can establish a potential difference across it. Okay. Now, an electron pair, that is the Cooper pair, you can say, experiences a potential energy difference of QV on passing across the junction. But you know Q is equal to minus 2E, because charge of one electron is actually equal to what? Charge of one electron is minus E, so the charge of the Cooper pair will be minus 2E. Okay. So in one region energy will be equal to 0 and another region energy will be equal to minus 2 eV, and therefore 0 minus 2 eV, in this way 2, you can say that this energy difference is equal to 2 eV. Okay, or in other words you can also say that a pair on one side has a potential energy minus eV and the pair on the other side is equal to eV. In this way you can also say, and so the energy difference will be eV minus eV, that will be 2 eV. Okay, now remember you have explained the DC Josephson effect and you have written the Schrodinger time dependent equation for the Cooper pair. Okay, so here when we will write the equation of motion, that is the Schrodinger time dependent equation for the Cooper pair of one region whose wave function or the probability amplitude is psi1, that will be given by IH bar del psi1 by del t, and that will be equal to H psi1 minus EV psi1. Mark it. When no voltage is applied, then this term will be 0, but here voltage V is applied and the energy of electron in that region is equal to minus EV, so we have to include this term. Okay, but you have seen that this H psi1 is equal to H bar T psi 2. You have learned already this fact in your previous lecture. Okay, here you know T is a quantity having the dimension of frequency or rate, and this H bar T represents the transfer interaction across the insulator. Okay, so instead of this H psi1, now you can write H bar T psi 2. Okay, and the second term is at each. Now for the Cooper pair in another region, you can write the equation of motion like this. This is IH bar del psi 2 by del t, and that will be equal to H psi 2 plus EV psi 2, because the energy of the Cooper pair in another region is equal to EV, not minus EV. Okay. Again, this H psi 2 will be replaced by H bar T psi 1. Okay. So you can mark the difference when you have written the equation of motion for Cooper pairs in case of DC Josephson effect, then this second term in RHS, that is the term containing the voltage, was not present, because in that case we have considered V equal to 0. Okay, so this is only the difference. Okay, now you have also learnt that we can express psi1 in this manner and psi2 in this manner. All these things you have learnt in the previous lecture. Here N1 N2 you know represent the concentration, okay, of the Cooper pair in first and second region, and this theta 1 represents the phase of the wave function or phase of the Cooper pair. Okay. Now as our equation of motion contains the term del psi1 by del t and del psi2 by del t, so from this these expressions for psi1 and psi2, first of all we will find the partial derivative of psi1 and psi2 with respect to t. Okay, so let us try to find it. Del psi1 by del t. See here. Here there is a product of two functions. First one is n1 to the power half and another is e to the power I theta 1. So following the product rule of differentiation, you can differentiate it. First of all, differentiate this n1 to the power half. This will be half n1 to the power minus half times del n1 by del t. And this factor, exponential factor, is at each. Now, keep this n1 to the power half at each, okay, and differentiate the another factor e to the power I theta 1, and that will be what? That will be I times e to the power I theta 1 times del theta 1 by del t. Okay. Now you can see this e to the power I theta 1 is a common factor, so we can take it as a common factor. So the resulting expression is like this. Okay. Now, this value of del psi 1 by del t, which we have obtained here, now use this result in the equation of motion 1a. At the place of this del psi 1 by del t, now we will use it. Okay? And psi 2 and psi 1 in RHS will be replaced by these values which we have defined here. So let us see. When you will put this the value of del psi 1 by del t in that equation 1a, your result will be what? You can see this will be IH bar, and del psi 1 by del t is this much. Okay? So this factor e to the power I theta 1 is here, and the remaining term is inside this square bracket. So I have written it here. Okay? And in RHS, you have seen that in RHS there is H bar T psi 2. So H bar T, and instead of psi 2 you can write this expression. You can see N2 to the power half e to the power I theta 2, and minus, there was minus EV psi 1. Instead of psi 1, now we will write N1 to the power half times e to the power I theta 1 from here. Okay. Now to cast this equation in a proper format, let us divide this result throughout by this factor. So you have to remember it. IH bar N1 to the power minus half e to the power I theta 1. Okay. So when LHS will be divided by this, you can see this IH bar e to the power I theta 1, which is present here, will cancel out. Only the factor N1 to the power minus half will remain, and that will be the terms inside this square bracket will be divided by this factor N1 to the power minus half. Okay. So when you will divide the bracketed terms by this N1 to the power minus half, your result will be like this. This is 1 over 2 del N1 by del t plus IN1 del theta 1 by del t. Okay. And now let us divide the both terms of this RHS by this factor, that is IH bar N1 to the power minus half times e to the power I theta 1. So let us see. When you will divide it here in second term, there will be 1 over I, and 1 over I is equal to minus I, and minus sign is already present here, so that will be plus. So I have written the second term first, and that will be IH bar N1 to the power minus half. Sorry, here they are written. So there will be I times EV times N1 H bar to the power minus 1. Okay. Here N1 to the power half are divided by N1 to the power minus half, that will be equal to N1. Okay. And now when the first term, this first term will be divided by this factor, then you can see this H bar will cancel out. Okay. And there will be 1 over I, which is minus I. So this is minus IT times N1 times N2 whole to the power half times e to the power I delta. Here delta, has been written instead of theta 2 minus theta 1. You can see this will be, this has been written in again for theta 2 minus theta 1, which is actually the phase difference. Okay. And so now instead of this e to the power I delta, we can write cos delta plus I sin delta. So other terms are at ease, you can see here, and instead of e to the power I delta, I have written cos delta plus I sin delta. Okay. Now on the same line, as you have differentiated psi 1 with respect to t, and then you have used this result in equation 1a. Okay. Similarly, when we will differentiate this psi 2 with respect to t partially and substitute that value in this equation 1b, just a result like the result defined in equation 2 will be obtained. And I am giving you a trick here to write down that very equation. Since instead of psi 1, now we are going to differentiate psi 2. Okay? And you can see the expression when there is psi 1, then there is n1 theta 1, and in case of psi 2 there is n2 theta 2. So you can think that when we will simply interchange the subscript 1 to 2 and 2 to 1 in equation number 2, then we will get the result which we have to obtain. Okay, so let us see. Here there is a term half del n1 by del t. So in this case, what will be the result? What will be this term? This will be 1 over 2 del n2 by del t. Okay, and here instead of theta 1 there will be theta 2, instead of here n1 there will be n2. Okay, and so you can see I have written it here. This will be 1 over 2 del n2 by del t plus I n2 del theta 2 by del t, and minus IE n2 V times H bar inverse, and minus IT times n1 n2 whole to the power half times cos delta minus I sin delta. Why minus? Because here there will be delta equal to minus theta 2 minus theta 1, because in this case you will have theta 1 minus theta 2. So there will be e to the power minus I delta, instead of which we will write cos delta minus I sin delta. Okay. If you remember the previous lecture of DC Josephson effect, you can see only the difference is here in the term containing the voltage. Okay, nothing else. Now we will equate the real and imaginary parts of the equations 2 and 3. So first of all, we are going to equate the real parts of equation 2 and 3 both. So let us see. In LHS, the real part is half del n1 by del t. And in RHS, when you will multiply by this factor IT times root over n1 n2 with this I sin delta, then I times I, that will be equal to I square, which is minus 1, and minus is already present, that will be plus 1. So that will be actually the real term, and that will be t times root over n1 n2 times sin delta. So you can see this del n1 by del t is equal to, here there was 1 by 2 factor, and that 2 has been multiplied here. This is 2t times a square root of n1 n2 times sin delta. And similarly, from this result, when we will equate this half del n2 by del t, then we will get t time minus t times root over n1 n2 whole to the power half sin delta. So del n2 by del t will be minus 2 times of this much. Okay. So these two results we have obtained by equating the real parts of equations 2 and 3. Now in the same manner, when you will equate the imaginary parts of equation 2 and equation 3, you will get these two results. I am not doing the algebra, you can do it. This is a very simple thing. This is the imaginary part n1 into del theta 1 by del t here, and in RHS there will be, this is the imaginary term, and this minus IT times this much times cos delta is also imaginary term. So when we will equate these, we will get that this del theta 1 by del t is equal to EV over H bar minus t times n2 by n1 whole to the power half cos delta. And in this case, the imaginary part in LHS of equation 3 is n2 times del theta 2 by del t. So when you will find del theta 2 by del t, you have to divide by this n2 in the terms in RHS, and that will be del theta 2 by del t equal to minus EB over h bar minus t times n1 over n2 whole to the power half times cos delta. Okay. So in this way we have obtained very important results. Now you know, I have told you in my previous lecture too that in general, for simplicity, we take the two superconductors identical. And if the two superconductors taken in this case are identical, then the concentration N1 and N2 will be almost equal. And if they are almost equal, you can say that this del N1 by del T, this will be then equal to minus del N2 by del T due to this minus sign. Okay. And now use the idea that N1 is equal to N2 in the two equations of this 5. Okay. So you can see when N1 is equal to N2, this N2 over N1 here will be 1, and here N1 by N2 that will be also 1. Okay. So del theta 1 by del T will be what? That will be EB over h bar minus T cos delta. And del theta 2 by del T, that will be what? That will be minus EB over h bar minus T times cos delta. Okay. So you can see I have written that this del theta 1 by del T is equal to EB over h bar minus T cos delta, and del theta 2 by del T is minus EB over h bar minus T cos delta. Okay. Now let us subtract equation 6a from 6b. It means you have to find del theta 2 by del T minus del theta 1 by del T. You can see when we will subtract the RHS of equation 6a from 6b, this T cos delta is the common term, they will cancel out, and our result will be minus EB over h minus EB over h. So that will be equal to minus 2 EB over h. But the LHS can be written as del T theta 2 minus theta 1, and that is equal to minus 2 EB over h. But you know, this theta 2 minus theta 1, this is written by delta, which is phase difference. So del delta by delta del T is equal to minus 2 EB over h. Okay. Now actually we will see by integrating this equation 7 that with a DC voltage across the junction, the relative phase of probability amplitude how varies. Okay. So let us integrate it. So let us integrate this equation 7. So you can see integral of d delta equal to minus 2 EB over h bar integral of dt between t equal to 0 and t equal to t. Now let us consider when time is 0, then this phase difference is delta of 0. So corresponding to the lower limit t equal to 0, I have substituted here delta of 0 for delta, and at t equal to t, we consider that the phase difference is delta of t. Okay. Now different integral of d delta will be simply equal to delta, and when you will put the limits delta of t and delta of 0, this will be simply equal to delta of t minus delta of 0. Okay. So delta of t minus delta of 0, this will be equal to minus 2 EBT over h. And so you can say that this delta t is equal to this much. This is delta of 0 minus 2 EBT over h bar. Okay. Now you know this del n1 by del t, which is equal to minus del n2 by del t. This rate of change of carrier concentration, this actually constitutes the current. Here n1 n2 actually represents the concentration of Cooper pair, and so the current constituted by it will be called supercurrent. And the current constituted is proportional to this rate of change of concentration. Okay, so the current can be given that this is proportional to del n1 by del t. Okay, del n1 by del t. And del n1 by del t, you can see this is equal to this much. Okay, so if we will consider the proportionality constant in which this factor will be also included, then that can be written as J naught. And so the supercurrent can be given as J equal to J naught sine delta of t. Here actually this J naught will definitely include what? This will include 2t n1 n2 over half. Not only this, but this will be a factor. So this J naught, which is actually the maximum value of the supercurrent, depends on this t. Okay, but this delta of t we have already obtained here. This is equal to delta of 0 minus 2 EVT over H. Now see this supercurrent density. Can you recognize it? When you talk about the alternating current, I equal to I naught sine omega t. Sine omega t a minus delta or minus phi, anything, any phase constant you can take. So here omega is the frequency of this alternating current. So comparing this result from the standard expression for alternating current, you can see the multiple of t, which is the angular frequency. What is in this case? In this case, that is 2 EV by H bar. So you can say that this result shows that the supercurrent is of alternating nature. It is an oscillating current, and it oscillates with a frequency omega, which is equal to what? That is equal to 2 EV over H bar. And this fact I have already stated earlier in the beginning without any proof, but now you can see how we can say that the supercurrent's frequency, angular frequency, will be equal to 2 EV over H bar. Okay. So if you want to find the regular frequency nu, that will be omega over 2 pi, and that will be 2 EV over 2 pi H bar. But 2 pi H bar is equal to H, which is Planck's constant. H bar is reduced Planck's constant. So nu is given as 2 EV over H. Okay. So in this way, we have explained how this applying the DC source or DC voltage across the Josephson junction, an alternating current is resulted, which is alternating supercurrent, because it is constituted by the electron pair, that is the Cooper pair. Okay. So you can say that this is Josephson effect. Now already I have stated earlier that this result permits to determine E over H bar from the relationship between voltage and frequency, as you can see. Okay. And frequency of the photon emitted when electron pair cross the barrier and a DC voltage of 1 microvolt produces a frequency of this much. Already I have told. You can calculate this value by this formula, that nu is equal to 2 EV over H, and when you will substitute the value 2 into 1.6 into 10 to the power minus 19, V is 10 to the power minus 6, and divided by Planck's constant, which is 6.63, 10 to the power minus 34. Then after simplification you will get this result. This will be 483.6 into 10 to the power 5 megahertz, that is 483.6 megahertz. Okay. So I think now the concept of AC Josephson effect is clear to you. Yes or no? Definitely you will say yes. Okay. Thank you very much.